So welcome back to the final session. And this session is on the intelligence wars. So I'm hoping for some combat. They're all a bit pathetic. They all like each other too much. I should get my brother on the panel, and then he'd beat everybody up. But so I might call on you just to be aggressive. But okay, I just want to make a statement, and then I'll introduce the panel quickly, and then we'll jump in. And the way I'd like to do this, I'll ask a question. I have a primary who I'll direct it towards. I'll open it up to folks here. And then if anyone wants to jump in, do so, rather than us going through the whole question set and then bring you guys in from the beginning. So here's the idea. I just want to tell you about the intelligence wars. And this is my characterization. So they are mental combat, right, over the best ways to understand the nature of intelligence. And I want to tell you about the kind of schools of combatants. So on the one hand, I mentioned the biological naturalists, and they argue that the most obvious and best way to understand intelligence is to study intelligent systems in the wild, intelligent systems that have evolved. And that's geneticists, cell biologists, neuroscientists, cognitive scientists, experimental psychologists, ethologists, the whole thing. The problem is that population is involved in a bloody internecine struggle. The neural people dismiss the cognitive systems arguments as ungrounded. The cognitive scientists are suspicious of the schematic logic of the experimental psychologists. The experimental psychologists are leery of the uncontrolled wildness of the ethologists, and the ethologists are contemptuous of the reductive naivete of the geneticists. So that's the real biologists. On the other hand, there are the functionalists, the computationalists. So they say that the only sure way to understand the way something works is to build one. And that observing things leads to confabulation and just-so stories. It's like reading a mathematical proof and convincing yourself you understand the theorem rather than proving it yourself. Okay? And that's all wonderful, but they also hate each other. On the one hand, and I hope they do, there's the symbolic, representational, low data, heavy algorithmic world. That's McCarthy, Newell, Herb Simon. These are people who try to teach metaphysics to transistors. Okay? And ultimately, everything that's interesting in intelligence comes down to logic. On the other hand, which is the dominant school today, is the big data, statistical, neural network, simple unit worldview. They bury their opponents in oceans of data, and they let loose on the world evil Go-playing algorithms. And around these two extremes, the north and south pole of combat, are the major sort of armies of opportunistic theories who are sort of waiting hungrily to pounce on any weakened or exhausted school of thought. Okay, so that's the landscape. And to debate that landscape, I have to go to the folks, is the panel. Now, since we're in Santa Fe, this is the home of George Martin. In case you don't know who George Martin is, you should leave. But he wrote Game of Thrones, and he lives in town. And I'm going to introduce people Game of Thrones style. Okay, so, and I'm not necessarily in this order, it's like this order. So, no, I sort of was a bit careful, especially with Jess, because he'd kill me. Jessica Flack, House Lannister. Professor at the Santa Fe Institute and the director of SFI's collective computation group, C4. Melanie Mitchell, House Targaryen. Professor of computer science at Portland State University and external professor and member of the science board of the Santa Fe Institute. Patrick Shafto, I'm sorry, man, House Greyjoy. Not good. Henry Rutgers term chair in data science and associate professor of mathematics and computer science at Rutgers University. Graham Spencer, House Stark. It's good, man. He's a trustee, you know, sort of managing partner, Google Ventures, Santa Fe Institute trustee, and formerly an engineering director at Google. I'm sorry, Brendan, man, but I ran out. Brendan Tracey, House Arian. Who? Anyway, they are a house. Postdoctoral fellow at the Santa Fe Institute, formerly a postdoc at the Department of Aeronautics and Astronautics at MIT. So that's the panel, and I asked all of them to prepare a brief statement on their position on this matter. And I'm going to reverse order, and I'll start with you, Brandon.
Yeah, so as mentioned, so my background is in aerospace engineering, actually, but I've done a lot of work on the intersection of engineering and machine learning and statistics. And so one of the things that I've been working on here is kind of this small data world where in aerospace we have these really expensive computer simulations that do a pretty good job of prediction. But we also have really cheap simulations that give us an okay answer. And so one of the questions is, how do you use these cheap simulations to help you inform when you should ask expensive questions? And similarly, maybe sometimes you want to use some of your expensive simulations to teach you something so that you can use that in the future. And the other aspect is things like an airplane have all these different systems that need to interact, but they're kind of easiest to analyze on their own. So the aerodynamics or the structures or the control system. And so how do you get them all to agree on the same worldview while all being individually happy and well designed? The other thing is I did part of my PhD on turbulence modeling, which is one of these grand open unsolved problems, and I did not solve it, spoiler alert. But what I was doing was we know a lot about how fluids move. The problem is that when we want to analyze that cheaply, we end up with these kind of pesky terms that we don't really know what to do with. And so what I was looking at was, how do we take data and try to make these models better without throwing out the physics? Because we know there are a lot of properties fluid motion has to behave. And so how do we keep what we do know while using machine learning to replace the parts that are kind of hand-tuned and ad hoc? And so one of the things that we were asked to talk about was areas that we felt could use more work. And I think one of the things is this validation and verification of these networks and how to make sure that they're constrained so they don't do crazy things. And in particular, in the aerospace world, it's hard to know right now how much of the progress that's been done, both on my work, but the stuff that's followed after it, how much of that is that we don't have very many data points. And so we're just tuning our models to get the right answer in these particular canonical flows where we do know the right answer. And so how do we know that this model we've trained on our few data points is actually going to give us a good prediction when we go to new cases, especially when even the real world is hard to estimate. Wind tunnels are noisy. The fluids simulations where we can't get the right answers are these conditions are hard, and we don't want to build an entire aircraft only to find out it doesn't work right. So how do we build these verification procedures in a way that's both not just satisfies the FAA in terms of what they think is safe, but also has some rigor and validation behind it?
Graham.
Do you want us to talk about this war-torn landscape
You
now?
introduce your own, your own very partisan, extreme view on
Okay. So my background is really starting with more of the high-level, kind of good old-fashioned AI, natural language processing, moving through machine learning, learning at Google more and more about deep learning, and then in my current role, we are trying to build different tools that will help our investors make better investing decisions. So I work at a venture capital firm, and our day-to-day is trying to make decisions about whether we invest in companies or not. And so we're very interested in trying to build different heuristics and tools that will help our investors make better decisions. In terms of my perspective on this landscape, I think I'm always, and actually, I guess I should also say that you asked what has been most interesting about these fields. I think the most exciting thing has been, at least from my perspective in Silicon Valley, seeing just the incredible pace of innovation that's happening in deep learning and in AI research. Many, many challenges still to be solved, but the pace of research is really overwhelming. You ask any researcher, they'll tell you that every day there's 30 or 40 new papers published, literally every day. They can't keep up. New results are being discovered and then shared over GitHub. Data sets are being created and shared amongst the community, and everyone is one-upping everyone else's results. So the pace of innovation is really, really incredible. And where I come down on this landscape is that what I'm most interested in terms of the research that's happening today is if you look at the divide between the connectionist approaches, the bottoms-up approaches, where you throw everything into a neural network and let it sort it out, versus the sort of more top-down logical approaches, I'm really interested in the very early work that's starting to show some of the logical steps emerge from the connectionist approaches. So some of the most exciting stuff that's happening, I think, is, for example, what's called the differential neural computer, or differential neural computing, where you have a neural network, but it also has an external memory, and it has a differentiable method for processing that memory. And so it's not unreasonable for me to imagine that a lot of what we look at as symbolic logic is actually emergent from the sort of what people call connectionist approaches today. So I'm happy to talk more about that in this conversation, but that sort of synthesis of those two extremes is what I think is really exciting.
Patrick.
My interests are mainly at the intersection of human and machine learning. I'm not sure where I fall in this fight, but I'll say one of the most things that I'm most excited about recently is thinking about cooperative inference. And that is a situation where you might think of a learner receiving information from someone who knows the right answer and who selects that information to help them as opposed to randomly. And moreover, that the learner also knows that they're in this situation. So this is the notion of cooperative inference that we're trying to leverage. And this is a formalization of theories that exist in the literature on cultural evolution as well as cognitive development. I think it breaks new ground in machine learning to potentially solve problems related to explainability and interpretability of otherwise opaque algorithms. I think it also potentially provides new ways of thinking about machine learning itself. That is, to think about it as a problem not just of inferring some latent structure, but also being able to successfully pass that structure on. And that yields constraints on the kinds of latent structures that you might entertain. And so I think, to actually put the fight in this, I think that the folks in cultural evolution are missing the boat. They have inadequate theories to actually support the things that they think they care most about. I think there's novel machine learning that is orthogonal in some ways to what people are thinking of in terms of just understanding machine learning, not just as a single problem, but as a system to pass information around as well as learn it. And this bears on a bunch of questions that I think are fundamentally of interest to society, including who to trust for information, as well as relaxing this notion of cooperative inference from someone who necessarily knows the right answer to more ecologically valid approaches such as guidance that can shed light into how having conspecifics around who are knowledgeable but allow you to explore might change learning.
So when I was an undergraduate, I read the book Gödel, Escher, Bach by Douglas Hofstadter. I don't know how many of you have read that book, but a lot of you, I think. And what the book, to me, was really about was how intelligence can emerge from a non-intelligent substrate via the collective activity of relatively simple agents. And I was so impressed and influenced by this that I went to meet Doug Hofstadter and asked to be a student. And after a lot of pestering, he took me on and assigned me the problem of writing a computer program that can make analogies using this kind of emergent architecture, if you will. So I got very interested in the whole phenomena of analogy making and its role in intelligence, and even more generally, the whole question of how we abstract meaning. And I think a lot of that has to do with understanding things by analogy. So there was an article written by Giancarlo Rota about Stan Ulam. And Stan Ulam said to him at one point, and I think in something like this, the 1980s, at what point will AI crash the barrier of meaning? And I think that's a really important question for AI. And the idea that there is this barrier of meaning, that AI can do a lot of things, like, as you saw, write bad poetry and so on, play Go, recognize images, design fonts, and so on. But somehow we as humans, at least those of us sort of familiar with these programs, feel that there's lacking of understanding and meaning in the program that we humans bring to the things that the same domains. At least some people believe that. And so the question is, what else does it take? And does it matter? Those are questions that I'm really interested in pursuing, especially in this meeting is one place to talk about that. Does it matter that we think that we understand the domains that we bring our intelligence to and machines don't? I used to think that it mattered quite a lot, but it was a big surprise to me. David asked us to say something that was surprising to us. It was a big surprise to me that speech recognition could be so good without having the machine understand what was being spoken. That was one of the biggest surprises to me in my whole career of AI, because I didn't think that could happen. And so that's a kind of a mystery to me, how that can work. I wasn't so surprised about AlphaGo. That's a very closed domain. It's very limited. But speech understanding is quite an open-ended domain, and so that was surprising to me. David also asked us to say something we found disappointing in the field that we felt was going sort of more slowly, you know, and as Graham said, there's 30 new papers every day, things are really moving fast in AI. But one area which is not moving very fast is the whole area of what people call common sense. Common sense reasoning, such as the idea that, you know, IBM Watson, for instance, could tell you how many gold medals Michael Phelps won, but if you asked him if Michael Phelps' hair was wet after he got out of the pool, it probably wouldn't know, because maybe that fact doesn't appear in Wikipedia. Or if you asked him if he wore socks while he swam. You know, things that are not explicitly stated anywhere, but somehow are the things that we humans learn by living in the world and seeing how the world works. And that's trying to imbue computers with that kind of knowledge has proved to be very difficult, and I don't think has really progressed at all. And that is, I believe, the biggest challenge. And I don't believe that computers are going to be truly intelligent in the sense that humans, at least, usually mean the word without that. But I've been wrong about some things like speech recognition, so who knows?
Okay, so the description I'm going to give about my interests as they relate to this so-called intelligence wars panel might make me seem a little bit like an odd man out, maybe not, we'll see. But I'm going to start this way anyway, because the perspective I want to get on the table is going to be important for some remarks that I'll make later in the conversation about collective intelligence, design principles, and possible similarities between artificial intelligence and information processing in nature. So what I want to do is just back out a little bit and go to a sort of popular SFI theme, which is the differences and similarities, of course, between physics and biology. So physics, of course, is dominated by concepts like pressure, temperature, and entropy. And these emerge through simple collective interactions, and they give us deep insight into the behavior of the universe. And biology and social science make use of comparable collective concepts. So metabolism, robustness, conflict management. But in contrast to physics, these are adaptive. They're functional concepts, right? And in addition, physics produces order through the minimization of energy, where adaptive systems, on the other hand, produce order and novel function through the addition of information processing, if you like, inference. So now we're getting closer to intelligence. So why adaptive systems have this extra step, and whether it makes them fundamentally subjective and uncharacterizable by laws or unamendable to prediction are obviously big open questions that certainly concern this panel. And we know, of course, from the scaling work of Jeffrey and Brian and Jim Brown and Luis, that there is variation in adaptive systems in terms of how much information processing there is. And in fact, that in systems with heavy information processing, the laws if we can call them laws, may in fact be different from the ones that are just dominated by energetic constraints. So, for example, as you all know, in the case of mass and metabolic rate, the scaling is sublinear, 3/4 power scaling. And in the case of the information processing systems like city size and crime and so forth, the scaling is superlinear. And the idea is that information processing is playing a role in this difference, right? And so maybe for the last 10 years, actually, it's quite a long time, David and I have been thinking about what it means to have heavy information processing in an adaptive system. And we think that in order to overcome the subjectivity that that entails, we need to think about how the system might be collectively computing solutions to problems that it encounters, right? So that's the collective computation perspective. And that's whether we're talking about molecular, neural, or normal conventional societies of individuals, and how they sort of solve problems in evolutionary learning time. Now, David asked us to address this issue of what we're sort of disappointed about or what motivates us. And I guess for me, this collective computation perspective is very much the how question. So how do we perform these computations? How do biological and adaptive systems do this information processing? Not why so much, which has dominated a lot of biology, but how. And so that's going to be my perspective.
Okay, good. So I'm going to do this in the following way. I'm going to ask the question. I'm going to direct it primarily at one person, but then I'm going to let other panelists jump in, and you all jump in, okay? So, but you have to sort of raise your hand, because otherwise, you know, I will kill you. So, okay, so the first one has to do with hardware, software, mind, brain, right? This very interesting rediscovery of the dichotomy in engineering, or maybe not. So this is really mainly for Brendan. And so in this recent progress in machine learning, in statistics, sometimes called AI, has it been largely driven by old algorithms that we've known about for decades, but with just the speed increments of hardware, and so there's nothing really magic happening here at all, or is there real ingenuity, which is sort of Graham getting at, in algorithm design, and the hardware is sort of not really relevant, it's just in some sense supporting the ingenuity of the software?
Yeah, I hate to have the stereotypical answer, but I really do think it's everything. So if you look at some of the data sets that are being used today, like they couldn't fit on a computer from 30 years ago. And so in that sense, it's a hardware thing that's happened. But I also think you sort of pose it as a dual question of like hardware and data versus algorithms, but I think it's more like a triangle. So like the CAPTCHAs that you've all been filling out, where what are these numbers, right? That was a largely Google, I think it was Google Maps trying to identify things. And now that it's working on self-driving cars, you're being asked to identify stop signs, right? Well, I mean, I'm not sure, but I'm guessing a lot of that is trying to find more data. And I heard anecdotally, actually, that Baidu, when they were trying to catch up on natural language processing, they had like a not mandatory task for their employees that they had to go talk for an hour and transcribe the data, just so they had more data. Mm-hmm. And so there's some view that neural networks are from the 80s, but I also think that it has been algorithmic. Things like these generative neural networks, to me, I think are quite new and seem really novel. And there have been a lot of advances in how to make these happen. And it's debatable whether these are incremental advances or whether they're new, but it seems to me that they're all necessary. So I think it's one of the things where we've hit different thresholds in the past where certain pieces are the constraint, and that has enabled and caused ingenuity on them. So for a bit it was hardware, then it was data, and now it seems like we're jumping back to the algorithms, but it's also the data, and so yeah, that's what I would say.
Anyone else here would like to address this issue before I push it out?
Sure, I think a couple things. One is that a lot of these algorithms are actually fairly finicky, and they can be difficult to manage and difficult to train. I had a conversation at one point with Ian Goodfellow, who's a well-known researcher in this field. And I'm not sure if this work is published, but he was saying that he, in his lab, they went back and looked at papers from the 80s using these old algorithms and tried to recreate some of the results on comparable computing hardware. And they initially found that they couldn't, but then when they made relatively minor changes, for example, the way that the weights of the neural network were initialized, then suddenly things worked. And so In some sense, that's an algorithm from the 80s, but in some sense, it's real progress in understanding what makes the algorithm stable. And I do think there have been, as you just said, there have been a number of really innovative algorithms, particularly in the past 5 or so years, whether it's adversarial networks, whether it's some of this differentiable computing. I think that people are starting now to innovate kind of layers above the sort of stack of plain old neural networks. All that said, none of this would really be that effective without things like GPUs, without massive clouds of hardware. Just one anecdote from a paper I was reading a month or so ago, someone was talking about tuning parameters for a recurrent neural network, and they said they used several CPU millennia of time to make that happen, right? And you can't make progress if that's what you need to make progress. Then you need a lot of computers. Yeah. So.
Anyone else? I did want to actually, is Chris in the room? Ah, he's at the back. Because I did want to push this out to Chris. So recently at SFI, we hosted a big meeting on quantum computing. And quantum computing seems to move, and you correct me, Chris, the argument back into the hardware realm, that somehow the hardware is going to do the work for us. I mean, do you just want to give a brief summary of that, and is that a correct characterization? Do you want to get a mic? Do you want a mic, Chris?
There's a lot of progress recently in quantum computing, and a number of technologies seem to be nearing the point where it will start to become scalable to 40 or 50 qubits, as we call them, which is roughly the point at which they can no longer be simulated or imitated by classical computers. These include superconducting technologies, like some of the ones that Google is looking at, some other wonderful exotic technologies, neutral atoms levitating, held in place by lasers, and ion trap computers, and so on. So on the one hand, I guess as a theorist, I think it's important to emphasize that quantum computers are not going to instantly solve all the search and optimization problems that we're all struggling with, including in machine learning. At the same time, it seems possible that just as we've gained a lot of experience in heuristics, the care and feeding of algorithms that work well in practice, if you figure out how to tweak them right, we'll probably gain some experience in quantum heuristics that we don't yet understand. What types of optimization landscapes are they good at navigating that classical approaches are not? So I mean, it's sometimes in the popular press you read stories that make it sound as if quantum computers will render all these problems trivial. That's not the case, but it will open up some new things. I guess I'm skeptical that it will change the fundamental issues that you all are trying to address, but it will be an interesting new world of computing.
Does anyone else want to comment on this hardware-software world? No. Good. Next.
Can I ask a question?
Oh yes. Where are you? I can't see.
Well, you have a whole raft of questions. I was going to ask.
Oh no, you go ahead, Chris. Yes, I do.
Well, so I appreciated Michael Nielsen's talk because I was one of the people who was, at some level, almost as upset about AlphaGo as I was about the election. You know, it was really a sense of loss, and what are humans good at anyway, if anything, and are we just rather stupid, easily deceived creatures? And so I like the picture of machine-assisted human intelligence. Hopefully, we still have something to bring to the table, as opposed to the machine just saying, "Oh yes, you should move the knight there. You can move the knight if you want, honey. Good, good. You moved the knight to just the right place." But one of the things which humans, a lot of humans claim that humans can do, is learn from a small number of examples. Now, people argue about whether we really learn from a small number of examples or whether we actually have a ton of examples stored up through evolution or through early childhood experiences and so on. So my question to you all, or whichever one feels like answering, is do you think it's true that humans can learn from small numbers of examples as opposed to 100,000 videos of cats? And if we can, do you think that that's an important research direction for AI to take?
I think, yes, humans can learn from a small number of examples in many cases, maybe not all. We're pretty good at building on what we already know, of conceiving of things in terms of what we already know. We're good at making analogies, if you will, which is a way to use what we already know to be able to do something else. I think, you know, if a human who's very good at Go, for example, would also be good at lots of other games that are similar to Go, whereas AlphaGo probably wouldn't be without a lot of retraining. I'm not sure if anybody's done that experiment, but I think that is absolutely key for AI, because it's not scalable. If we want AI to learn all about the world isn't labeled. The world isn't, you know, very carefully curated in terms of training sets and test sets and so on. And so it has to. And you know, I think Patrick mentioned that he's looking at cooperative learning, where learners actually choose the examples to learn from. So I think in the machine learning community, people call something like that active learning. And that's also a way that humans are good at learning from a small number of examples, is that they choose examples that are particularly informative for what they want to learn, and they seek them out.
Or the social environment is set up to help them establish those correlations, which is very much a kind of cooperative inference point.
Yeah, so for example, infant-directed speech is a classic example in cognitive development, where people produce, I'm sure everyone's seen this before, right? People talk funny to babies. There's a question as to why. Why would you give atypical input to someone that you wanted to learn the language? And one theoretical account that we've proposed is that they're actually optimal in a very precise sense. And so the goal of the interaction with your child, at least implicitly, is to provide them good examples to infer not only how many categories there are, but where they are in phonetic space. And so we can quantify that hypothesis and in fact, at least to a coarse extent, confirm some counterintuitive predictions. And so I think this points to actually a very big set of answers to your question, which I think is a very good one, is that, you know, small is relative to the size of the space that you're trying to do inference in, right? And so a lot of the fights about smallness just are disagreements about what the size of that space actually is. But also, the way in which the examples are produced matters a lot. And so, you know, machine learning algorithms are trained on, you know, ostensibly randomly selected examples that are labeled correctly mostly. Right? So it's a classic supervised learning case. But human learners receive large amounts of input from people who behave systematically, who have goals and intentions. Sometimes those goals are to actually help you learn as the learner. And so I think in all of these ways, sort of the smallness of the data is sort of a little bit of a red herring. Of course, it takes hopefully less data to learn in those contexts, but it does so for a sort of counterintuitive reason, which is that the space of possibilities is opened up. That is, you actually simulate not just what the data are, but why the data came to be in front of you in the first place. And so I think these are sort of complicated answers to a very good question. And I'll add one final point, which is that human learners do learning inside a human head, which doesn't generate much heat. This is sort of an obvious point, but it's a huge difference, right? So small is both an example-based question, but also an energetic question that I think has been not as well addressed, but is arguably even more important for the long-term success of machine learning and AI.
David?
Yeah.
So a sort of follow-up for Graham. If you know this, you're the token Google guy here. When Google looks at a street number, for example, is it simply doing that image processing, or does it also have a set of rules like check for which side of the street you're on, or look at what the numbers might be in the vicinity. How much is it simple image recognition versus all kinds of modeling around it? And has it improved?
It's a good question. I don't really know the answer to it. I guess I would conjecture that when it's at the level of a car, an autonomous vehicle, that a lot of different information is being pulled in as a way to kind of double check and cross check the information that it gets. I think in that particular instance, it's really just about training a number recognizer without a lot of other helpful information. But I don't really know.
Raise your mic a bit.
Oh, sorry. I did want to come back though to Chris's question also. So I definitely agree with what Melanie said about the importance of whether it's sort of one-shot learning or transfer learning. These are some of the phrases that people use. I think it's not it's understood that it's a problem with current AI techniques. I think there is a little bit of interesting and provocative research in that direction, so I'll just mention a couple of things. One is that people have started to do work on sort of one-shot image recognition. So if I show you a picture of, if I show you 1,000 pictures of a cat and 1,000 pictures of a cow and 1,000 pictures of a frog, and then I show you 1 or 2 pictures of a dog, can you successfully identify the dog based on regularities and the other things that you've seen? And so there's some progress in that. I think another interesting area is talking about whether AlphaGo could play another game that was similar. It probably couldn't, but there are researchers who are looking at this arcade learning environment, which is the DeepMind Atari games, and trying to basically train. It's somewhat artificial, but it's sort of a 2-level hierarchy, where one level is kind of learning actions that you might presume to be reusable across different contexts, and another layer is learning how to string those together. And so what you find when you build systems like that is that it takes them a while to learn the first set of actions, but then those actions do transfer a little bit more like what you might expect a human to do. There's a long way to go, but I think that's a pretty provocative step in that direction.
I mean, one thing I'd add to this is the comparisons are often, maybe this is what you're getting at, Patrick, unjust, because you, when you learn, have 100 million years more of evolution plus a year of learning. And the question is, what did evolution give us? And it's a nice example, actually, from talking with Google Research, where they had a failure. And that is, I mentioned this to Tommy earlier, they were trying to teach an algorithm to recognize biomolecules. And because all of these algorithms are very good at encoding planar images, they'd show a molecule, they'd rotate it slightly, you'd have to learn that as a separate molecule. Rotate it again, it's a different molecule again. So we have a notion, it's called rotational symmetry, some invariance principle. So my guess is what evolution gives us is symmetries, not contingencies. And we use the symmetries to organize them. And so it's that combination between the fundamental principles of evolution and the contingencies of learning that make, and I don't know if you guys agree, us a bit special. And it may be somewhat different from these learning algorithms.
Yeah, and to add a little bit to that, with what Graham was saying, so one thing that humans have, as you were saying, is like we have language and we have a really good object system. So when you tell me that this is a water bottle, I can kind of infer what water bottles might be, because I know what water is and I know what a bottle is. And so combining those isn't so hard. Whereas in contrast, something like Go, humans don't learn very well with small data, right? In order to become a professional Go player, it takes 20,000 hours or more of playing Go in order to figure that out. So I think there are certain problems for which we are really good small data learners that build on these other tools. And similarly, as far as I understand, there's work now that's showing if you take a neural network and you train it on language and object recognition at the same time, it kind of magically does better at both relative to systems training each individually. And I think that kind of comes to this. And then there's a third thing, which is that oftentimes we demand of computers higher standards than ourselves, right? So when we say we understand Go because we know shapes, it means like there are some things that we can talk about it, but it's different than playing at as high a level as we want the computer to play at. Or if I say I understand what some fashion item is, but then I forget it the next day, have I really learned? Whereas we'd want the computer to not forget. So I wonder if that higher burden of standard is also why we're forgiving of humans being small data learners, but not of computers.
So I want to ask a data question. It's a Graham question, which is to do with the sort of saturation of the performance on these algorithms based on the saturation of the data set. So in some sense, it's a well-known regularity that they're as good as the regularities in the data, right? In other words, the more data you feed them, to the extent that they can compress and extract, the better they get. But at some point, you're going to run out of the regularities in the data, presumably. And will that be it? So are they essentially just echoing back in their own language the compressed regularities of the signal, or are they doing more than that? Which gets maybe to Michael's creativity question. Where's the creativity here?
Well, I mean, let's see, can you hear me? I don't know that we know yet. I mean, I don't know that we certainly don't really fully understand human intelligence, nor do we understand exactly how these algorithms work. I do think that, I think you can go a long way with just compressing regularities. I think that, Melanie mentioned a little bit ago unsupervised learning versus supervised. I think that's an area that a lot of researchers in the field are deeply interested in, because it's understood that there are only so many regularities in a labeled data set that you can extract. And I think some of the sort of quirky things that neural nets do today are in some ways, I think there's a suspicion that it's in some ways due to the fact that they're trained on fairly idiosyncratic data sets. I think that the very famous researcher Jan LeCun, who is one of the leaders in the field, he gives an analogy which he's been cited a lot for, which is the sort of, there's a cake, and deep learning is the whole cake, or sorry, unsupervised learning is the whole cake, and supervised learning is just the icing on that, and then reinforcement learning, which is what we're doing with the Atari games, is just the cherry on top. And he's really trying to encourage people to spend more time on, he's now using the phrase predictive learning, which doesn't necessarily mean in the future, but it means tackling tasks like, if I show you a picture of a person's face and I cut out the upper corner of it, it's pretty easy for you to predict what's going to be in that corner. So you're predicting basically the input from itself. And so I think a lot of people believe that that's a really important direction. And I guess the last thing that I would connect that with, if you sort of connect that, the cake to the cherry on top, another interesting area of research that I'm really excited about is what I think people are using the language a little bit too figuratively, but it's imagination in machine learning models, where one thing that we know that humans do is we plan. So we imagine a scenario, and we think about how our action might unfold in the real world, and then we go back and we do it, and then we learn about was our model of the world correct or not. And reinforcement learning generally doesn't do that. It generally just does it and then sees what happens, and then it does it again and does it again. So there's been some really interesting research in terms of having a system simultaneously build a model of the world, which is its imagination, and deciding whether it's going to plan ahead in its model or whether it's going to actually do an action in the real world. And so, yeah.
So when you said predict the input from itself, is that basically like you have a sparse representation, you use some kind of like compressed sensing approach to reconstruct the full input, something like that?
It's sort of agnostic to what's happening in the middle, but it's, if I give you an image and I ask you to predict the same image, but I put constraints on your representation in the middle, so that is it, are you compressing the representation somehow and then regenerating it? And that's kind of that's the idea. So.
So human belief systems can be rigid, and to what extent might you occur that as well in artificial intelligence?
That's interesting. I think, I could imagine in in an Atari reinforcement learning setting, you're playing the game Breakout, and then the rules change, right? Would a reinforcement learning system learn that, or would it just keep failing? I think a lot of it depends on, sort of the momentum, if you will, of the rules that you've learned about the system and how quickly you let those change. I don't see any reason that you couldn't allow your beliefs or your model of the world to sort of change over time and to adapt to what it's seeing.
But it seems to me the question is, the reason why you get persistence of belief in human institutions has to do with social power, right? It's not just the limitations of inference, generalization, and updating. It's, I don't want you to have my land, What about the strategic, maybe that's the deeper subtext, what about the strategic desire of the algorithm or the AI to maintain control in some minimal way that would correspond to the propagation of a power structure?
Well, I think you have to start. That's a little bit too far along for where AI is. You have to even start with AI systems don't have belief systems at all. They don't have beliefs. They don't have motivations. They don't have the kinds of emotional attachment to things in the world that we have. So the question is, if they had those things, at that point, what could they become more human-like, and then kind of get into a belief bubble of the kinds that we get into, or not. But I think that's a little bit too anthropomorphizing, AI systems.
Even if you would have basic laws that you would want to give as input to create a general AI, for instance, and then the basic laws over time would not be upheld.
So, I mean, there's a trivial level at which this is true, where like if your model is a linear model and that's all your model can be, and all you can do is tune what the slope is, like in a surface level sense, that's beliefs that the algorithm can't update. And so if there are these things that you kind of build in directly, then sure. I'm not sure at a deeper level though, like for instance, a lot of these belief systems that cultures determine at one point were a good idea, and then the cultural follow-on sort of keeps them in place, as opposed to understanding that the underlying surface has changed and we should update. And so this kind of goes about the Atari game where, like, I don't know, if you've programmed an algorithm that this is how you should update your beliefs in order to get the score, but to get the highest score, but then all of a sudden you switch it and now it's trying to play golf and get the lowest score. Right, that kind of thing, it would probably be terrible at golf because it knows that it's trying to maximize the score, and you've hard-coded that in, right? But I'm not sure how deep that is in the sense that you could also just say win, and now as long as you don't all of a sudden change it to wanting to lose, a lot of these systems can be quite adaptive to new data, and so can respond to underlying environmental changes. But there are these paradigms that are built into the algorithm that are harder to.
Yeah, I'm just wondering. I mean, it seems not as sophisticated as you suggest, Melanie, because we know about preferential attachment and these kinds of positive feedback effects that tend to produce lock-in, and it's happened in algorithms. I mean, it sort of happens with web browsing. There is a kind of inertia of the kind you're describing in search, right? So it's sort of there in a zeroth order form, not in the strategic form, but by virtue of the way that you learn, right? So anyway,
I'd like to disagree with the premise a little bit.
Okay. Good.
Sorry.
Getting closer to
yeah,
battling,
well,
but it's good.
I'll supply some of the disagreement. I don't agree with the idea that humans are especially rigid in their beliefs. In particular, it depends on the scale at which you wish to frame that, of course, and I'm going to frame it in a way that benefits me. But I think the basic point is that young children are actually quite not rigid, right? You can take kids from one culture and move them into another, and they will adopt the language, the belief systems, and everything. And even if they remain in a single culture, they're not necessarily particularly obedient to their parents' wishes. In that sense, on an individual level, at least for young children, there's quite a lot of adaptation, and I'll put in a plug for Alison Gopnik's talk tomorrow, where I think she'll at least reinforce a few of these ideas. But I think the bigger perspective is that humans as a whole are built such that we die and new ones come about, right? And so that induces change in belief systems. And I think in that sense, maybe you would be correct, right? Which is that we are just accumulating data right now, which is fine if you think that the world is a stationary target, but it's not necessarily fine if you think the world is changing, right? It behooves you to periodically get rid of all the old data. And so I don't know to what extent people have thought this through, but certainly understanding the dynamics of the world becomes important to avoid these kinds of lock-in problems that would be concerning.
So I did have a question for you, Patrick, which has to do with the way we learn. So I know that Alison will talk about this, and you talk about this, that most of us, grew up and we learned very different things when we were 3 and 2 than we learned when we were 10, 15, and so on. And I know there is a move in the machine learning community towards this sort of developmental, creche-based AI. I just wanted you to comment on that, and what is the value? Is the fact that we learn developmentally a contingent fact of biology, which we'd rather not have, just happens to be the case, and if we didn't have to replicate that, why should we? Or is there something about the way that the information is presented, of the sort that you just made, that actually makes it a better way of learning, actually aging from infancy to adulthood?
So I think the overall trend of machine learning paying attention to cognitive science and developmental science can only benefit machine learning. And the reasons are that there are people that have been thinking about humans as a model system for a long time, very smart people who have come up with lots of clever ways of testing hard questions and getting answers to those questions. And so there's a lot of knowledge there to be leveraged, for sure. But I wonder about the depth of the interaction. So at least if you go back to good old-fashioned AI, this was also true. People got interested in cognitive science and development. But in many ways, there was simply a bifurcation, right? So people in machine learning might be interested in, my deep network can do X. And I think that's deeply uninteresting and probably a negative trend. I think there is a lot to be gained by the synergy between the two. So what I mean by that is that it is important for machine learning folks to actually care about the inductive biases that are built into children and ask whether that is a good or bad thing. So this is sort of what comes built in. And also look at the structure of the environment and how that organizes the kind of data that children encounter and how that changes over time with development. So both of those are probably important contributions. But I think it's also true that there can be big contributions in the other direction. So one of the striking things, for me at least, about developmental science is that there's people are wonderful, excellent in their ability to actually ask precise questions about very, very hard matters. But there's a lack of knowledge about what kids actually do. Right? We just don't have a lot of data of like what they're doing, and we don't tend to pull insights from that sort of observational data. And of course, that's a huge and hard data analysis problem. There's a good reason for why that's so. But recent advances in machine learning start to put that in range, right? So in the sort of trivial case, you could set up classifiers with deep networks to automatically code different kinds of learning episodes in classrooms or in homes. And this, I think, would benefit developmental science fantastically. And surely certain elements of these things are happening already. So I think there's a big synergy to be exploited there.
Can I just make a comment? So in response to the question, like, do we have to learn things in a certain developmental way? I think the question, it really depends on what kinds of things you want in the end, for the outcome. So understanding natural language, that's something that kids learn to do, and we really want machines to do, or at least some people want machines to do. Well, people have pointed out, as one example, that George Lakoff has done a lot of work on how language is built upon metaphors that have to do with the physical, our interaction with the physical world. And learning about how our interactions with the physical world is sort of what babies spend all their time doing. And so I would hypothesize that being able to do that is really a prerequisite to a human-like understanding of natural language. both at the level of just basic language and more abstract, metaphorical kinds of concepts. So.
Yeah, that's done.
I was sort of, thank you, Melanie. I was sort of wondering that when Graham said he knew what a bottle was and he knew what water was.
He said that.
Oh, sorry, yeah. And I can't even recognize people, let alone objects. But this is just a practical question. Is there an ontology out there that people can use from that, where does a machine go to find out what a container is? And then there's a container that's closed or a container that's open. There are liquids. I mean, how much of that understanding is actually encoded somewhere? I mean, I know there are machines and robots that do stuff, but is there any kind of generalized?
So there's been some attempts by people to encode sort of common sense,
the world,
if you want to call it that. So, Doug Lennon is a famous one.
But it was all words. It wasn't.
It was all words. Right. So the question is, how do you encode it? And I think nobody really knows. There's a guy named Josh Tenenbaum at MIT who's looking at how could we get machines to kind of learn intuitive physics. But it's very, very preliminary, I think. And I think that's really a big open question about AI is how do you get AI systems to learn the basic things about the world that we take for granted? And I don't think anyone knows the answer to that.
Can I just...
What?
Or has built it. The way you would find out the answer is to try and build it.
Okay.
A functionalist.
I think that some of the provocative work in this area is, for example, trying to learn common sense physics behaviors from YouTube videos. So, how many videos are there out there of, cats jumping or falling or, kids playing or whatever? And so you can actually go and watch those videos and see if you can infer interesting things about physics. I have no idea if that approach will work, but I think it's interesting.
But it might be quicker just to have a model that includes the laws of gravity and some stuff like that.
But also there's some pushback. I think it partly depends on what your definitions of understanding are and what your kind of measurements, again, as a functionalist perspective, where if I haven't tried this, but I imagine if we asked Google, like, could you please bring up the price of Bratz toys? It knows that Bratz is spelled B-R-A-T-Z and not B-R-A-T-S. And this is not just because Bratz is like a really popular thing, right? If you ask it about place names in Santa Fe, it can oftentimes pick up the particular store that has this weird spelling versus that. And so the system that is my Android phone does have some geospatial understanding and is able to do things. Now, is that really natural language understanding? I'm not sure, but in terms of me asking a question and getting it directions to where I want it to go, it's remarkable how good these are. And some of these general networks where I want a picture of, we kind of showed this morning a little bit, like I want a picture of a flower that has blue petals, and it generates that. And like there's something like understanding, certainly, whether we define it in the same way we define it for humans or not.
Can I ask, in the interest of time, because I know I'm running out of time, I do want to ask this question about collectives. Most of us were trained in an extraordinarily individual, organism-centric way of thinking about intelligence. I mean, every discipline, psychology, sticking someone in a scanner, IQ test, it's all individual-centric. And yet we know, based on the talks you've heard this morning, that actually that's probably like 1% of what it means to be smart. And that 99% of what it means to be smart was given to us through infection, right? Through learning, through culture, through the mathematics, through the language. And so it's a question for Jess, right? What's missing? What whole new set of theories do we need to understand collective intelligence that's sort of missing from 99% of the discussion?
Well, I guess the first point is that, at least for me, the focus on individuals in the intelligence literature is just very weird. So if you look across adaptive systems, you see that almost all of them are collectives. And what do I mean by that? Well, it's, of course, obvious in the case of human societies, obvious in the case of animal societies, social insects. But it's also the case for every entity, more or less, that we refer to as an individual. You can think of every body, every brain is composed of multiple noisy components, right? Cells, neurons, they're all processing noisy data. And if you think about the decisions that we make all the time, whether they're binary or complicated, every single decision we make is in some sense the outcome of a collective neural computation, right? So the question, as far as I'm concerned, is how do all these individual or component level decision-making rules and strategies combine to produce some coherent output at the whole organism or whole society level? And you can sort of approach this problem by thinking about how those strategies combine in terms of circuits. That's how we approach the problem, but it's not just us. So they can be neural networks, actually. They can be gene regulatory circuits that map genetic material, genetic interactions to phenotype. They can be social circuits that map individual decision-making rules to social structure. And in our work, what have we gained from thinking about the problem this way? Well, one of the things that we've sort of recently hit on, but that's sort of come out of actually years of work, is that we discovered that collective computation, one universal or maybe quite generic feature of it is it seems to have two phases, an accumulation phase and an aggregation phase. What do I mean by that? Well, a collective has multiple, like I said, noisy information processors processing noisy data. And what they do is each of these components goes out sort of semi-independently and collects information or extracts regularities from the environment. And the information is, of course, not perfect. And then that takes sort of a long time scale to do that. And then they come back together, and that information gets essentially shared. And it can be through a kind of like collective process where the information is actually discussed, and then the system produces a single coherent output. Or it can be collectively, the information is sort of collectively encoded in the network of those interactions among the components. And in that way, some coherent output is produced. So we've seen this process, these sort of two phases in both neural and in animal social systems, and in web search. So that seems to be a kind of interesting generic principle that might be a feature generally of collective computation. And we've also discovered, as part of this, that the computation can have levels or layers. So in biology, we talk about levels of organization. That's what I'm talking about here. That arise through coarse graining and compression. So compressions come up a bit. Coarse graining is just essentially a kind of lossy compression where you look at some data and you extract the sort of fundamental features. Think about a painting, like a pointillist painting, and you're close to it. It doesn't really make much sense, but as you step back, you get the general essence of it, right? That's kind of what coarse graining is. And so we've sort of seen in the systems that we work on that you get these layers emerging of increasingly coarse-grained or compressed representations of the input data. And in some cases, there's even feedback from these coarse-grained representations back to the microscopic level, the individual level, that changes the strategies they use. It actually often reduces the variance in their behavior. And what this does on the sort of whole is decrease uncertainty in the system about what the good strategies are. So there's a kind of increase in mutual information between the input, the microscopic behavior, and the output. And now, I don't know if anyone's with me here, but what does this sound like? So most of you probably attended the morning session by Artemi and Brendan. So does anyone want to make a guess about what does this sound like to anyone? Come on, someone be brave. Deep net. Did someone say that? Exactly. That's totally right. That's where I'm going. So so it sounds a lot like neural networks. And in fact, so that Brendan and Artemi described that this morning. And of course, there's looking over the last year at the sort of neural architectures out there, you can see these beautiful drawings. I'm looking at these things and thinking, well, actually, those look a lot like the systems that I work on in biology. And so how can I understand this? What is going on here? And so I guess what I'm pushing, and I'll come to the principles again in a second, is that our sort of perspective is by comparing the biology, the adaptive system information processing, to these neural networks, we might be able to come up with some design principles. So Artemi said this morning that in the machine learning AI community, it's a little bit ad hoc. You sort of add this, you add that, and you see what happens. Well, it's possible that by doing this comparative thing, we might be able to come up with some design principles that way, and then try to build these systems with that information in mind. And just to make this a little bit more concrete, so where is this coming from? Well, for me, it started with this paper by these two physicists in 2014 showing that there's a mapping between what's called in physics renormalization and deep neural networks. And what we need to know for this discussion is that the renormalization just allows for iterative coarse graining. So essentially these layers and layers of coarse graining. And there's lots of technical issues there, and there are people in the room who know way more about this than me, Artemi and Brendan and David Wolpert and so forth, and Sid in terms of coarse graining, so you guys jump in if you want. But it's starting to look like this sort of structure that we see in biology. And then a computer scientist by the name of Tishby, who did some work with Bill Bialek, who's a physicist who's been out here a bunch, in 1999 on this thing called the information bottleneck, saw this Schwab paper, this physicist paper on renormalization, and thought, well, The information bottleneck is a lot like that, but it's about compression. And so he came up with the idea that actually deep neural networks might be doing this sort of information maximization, what I described earlier, maximizing the mutual information between the input and the output. And in doing so, building these layers of these compression layers. And so in addition, what Tishby suggested, and his collaborators, is that there are two phases to this information bottleneck approach. One is a fitting phase, where you learn the neural net learns the labels, and the other is a kind of compression phase, and that's what allows it to do generalization. And when I read that, it started to look a lot like what we think about, to me anyway, information accumulation, information aggregation. So this is all very preliminary, but it's kind of exciting in the sense that by doing this comparison, we start to see there might be these principles that sort of are governing how the neural nets and how biological systems or adaptive systems are finding ways to do this uncertainty reduction, this information processing. Should I stop?
Yeah. No,
I don't want to stop.
No, because that's a lot to absorb. And so I'm gonna. That's a good moment to end, because I think I'm going to test you all on what Jess said at the Institute. But maybe we have a couple of questions. Yes.
Is it on? Yeah. I was wondering, and this goes very much, I hope, to what you're saying, where does instinct come in? I mean, we have to learn how to walk and crawl and whatever. But a turtle just comes out of the egg and does it, and swims towards the sea, knows what to do. Does biology already know enough about that kind of knowledge to use that for AI?
Well, I think David was making this point earlier, that evolution has built into our brains a lot of machinery for information processing. Mm-hmm. And so we have already these shortcuts and computational machinery there to deal with certain kinds of problems that, in fact, we don't have conscious access to. And I have seen, and you guys know, I mean, I have seen in the AI discussion this debate about whether there should be innate machinery built into neural nets. And I'm not exactly sure what that would mean. So maybe that's something to sort of elaborate on.
There was recently a debate between
Right.
Gary Marcus and
Right.
Jan LeCun on that very topic.
Yeah. So what would that mean in the neural net case? To have some sort of
I guess it would mean that it has some prior knowledge built in, or some ability to access some knowledge structure. But I don't think anyone knows exactly how to do that.
There's very, a very crude version of that would be in most of the neural networks used for image recognition. They're convolutional neural networks, and the convolutional structure of the network is a way of expressing the fact that we know there's symmetries in translation, for example. So when an object moves a few pixels over, it's still the same object. And so in some ways, we're sort of cheating with the convolutions, because we're building in, I mean, if you're a purist and you wanted the network to figure all of this out by itself, it would maybe take a lot longer.
Well, it would take 4 million years of evolution, right?
Yeah.
I mean, billion years. Sorry.
I think the problem, the debate is a little bit of a red herring, right? Because neural networks have inductive biases. We just don't understand them most of the time, and so, when we're building in convolutions, we're explicitly doing that because we happen to know sort of how to make that work. But I think the fundamental problem, and why that argument continues to happen for decades, is that we don't understand what we're building in when we're building them, and that seems to be a good thing at the moment, in the sense that we can learn lots of interesting things that are difficult or intractable with other more explicitly representational approaches. But I think there's a real danger there. And one that's been exposed by a lot of the recent work in adversarial image generation and so on. If we don't understand what it's doing, we should be very concerned that someone else will exploit its weaknesses.
I like that. So on that very dark, can I end on that dark? Go on, jumping quickly.
Well, I just wanted to respond to some of the stuff that Jess was saying, because I think that it's important to point out that one big difference between the biological systems and current deep neural networks is the feedback aspect that you talked about, where the different layers can feed back to one another. And I was told by a neuroscientist that, for instance, the visual system has 10 times more feedback connections than feed-forward connections. Mm-hmm. And nobody knows exactly why they're there. There's a lot of regulatory stuff that has to go on. And that's idea, which is fundamental to biology, is really lacking in current approaches to neural networks for the most part.
Are there some new papers dealing with that now?
there's work on recurrent neural nets, but that's not really the same thing. You know? So I think there's some things from the biology that still could be really beneficial to understand why they're there in biology, and then
I did see, and it could just be that I'm misunderstanding, but I did see these a few papers that do this compression, and then they feed the compressed output back down to the microscopic level, and that constrains the microscopic behavior, which sounds to me, on the surface anyway, a lot like what I see in the systems we work on.
So I'm just going to spare the audience, because you know, it's a wonderful day, and I just want to make sure I get all this. I'm going to turn it over, before I turn it over to Will to give the logistics, let's thank the panel very much for their contributions. And,